What's good, everybody? My name is Professor Jennifer Hill, and I run Divide and Conquer Math, which is both a website and a YouTube channel dedicated to helping you learn math on your terms. And this is my Study with a Math Professor series, which is dedicated to helping you really study for a math test. So this is the second video in my derivatives series. So this video is really dedicated to problems of like a medium level of difficulty or an average level of difficulty. So kind of hard, but not super basic, but not the hardest thing. So I think this kind of gets us warmed up for very difficult problems. So for these videos, you need a problem set, which you can find a link to in the description below. It's totally free. That problem set has not only the whole set of problems that I will go through in this video, but it also has all the answers so that you can check your work and then you can just quickly find the answers or you can watch the answers that you need. And I also have a suggested video list for each problem. So if you're working on a particular problem and then you realize, oh, I kind of forgot how that works, or oh, I'd like to see another explanation of that, don't worry, I've got you covered. So everything's kind of laid out in that problem set. Now, when you grade yourself on that problem set, if you realize that you got a problem wrong and you could not figure out why, then you can look in the description of the video, you can find that problem number, and then you can just fast forward and watch the whole solution laid out and then decide what you want to do from there. So the first hour of this video is dedicated to just study time. I've got that set up in case anybody has kind of motivational problems getting started. So I will give you 1 hour to study. I don't expect you to necessarily finish the whole problem set. So if you didn't finish it, no worries. You can just pause the video or go back and start the timer over. Whatever you want to do is fine. And then after that, then I'll just go straight through the problems. Now you'll notice that I don't teach you how to necessarily do problems because this is really a review video. So you're kind of expected at this point that you've kind of been keeping up with things, and now you're really just trying to get prepared for a test. And you know, my philosophy is practice, practice, practice. So if you've never watched my video on how to study before, there is definitely a link to that in the description below. Okay guys, so let's get started, and leave me a comment if you find this helpful or if you have any suggestions on how to make it better. Thanks for watching, let's go. Okay guys, so I'm going to start the problem set. So if you're not done, you can hit pause here or you can start the study video over again. So for our first problems, we want to use the formal definition of the derivative or the alternative formula, either one, to solve the problems. So for our first problem, we've got f of x equals 1 over x. So for this problem, I can use either one of these. So I've just got the formulas here. So if you want to pause the video to write those down, there you go. So I don't think there's like an advantage to using one formula over the other. So I'm just going to use the definition of the derivative. So just the original formula. So the first thing that you always want to do is write it down so that your teacher's like very clear that you know what you're doing. And then it's just a matter of plugging stuff in. So in green, I'll do f of x plus h. And then in pink, I'll do f of x. And notice how I'm going to stay really consistent with keeping my limit notation because I haven't actually evaluated the limit. So here's f of x plus h. And then here's just f of x. So there's one minus the other. All of that divided by h. So from here, now it's just a matter of trying to simplify this as much as you can. This is really just like a complex fraction in disguise. And if you forgot how that works, I do have a review video for calculus students on complex fractions, so you can look that up. Or I'll drop a link to it in the description, I guess. And so the way I like to approach these is I like to just clear out the denominators. So when I look at these two fractions, what is the least common denominator between those two fractions? Well, that would be x times x plus h. That would be my LCD. Now, whatever you do to the top, you also have to do to the bottom. So it's kind of like I'm multiplying now by really this fraction. So now let's just take a moment to think about what happens when we distribute this. So I'm gonna go ahead and set up the next line of the limit so I can kind of fill this in. Okay, so as I distribute this, so I'm multiplying this against this whole thing right here, right? So what's going to end up happening? The x plus h is going to drop out, and so it's going to cross out with this x plus h. So I'm just left with what? I'm just left with x. And then for this other one, so if I take 1 over x times this whole thing, so as I multiply this now against this piece here, the x's will drop out. So what am I left with? I'm left with just, x plus h. Okay, so that's the top, and now the bottom is going to be xh times x plus h, okay? All right, so now, let's see, I think I can finish this over here. Okay, so now I've got to simplify the top. So notice I'm going to have x minus x, right? So the x's are actually they're gonna drop out. So I'm just left with this negative h on top, and then I've got all this other stuff in the bottom. And so now I see that the h's also drop out. So what am I left with now? I've just got this limit as h approaches 0 of negative 1 over x times x plus h. And now I can't simplify any farther. And notice now if I try to plug in h equals 0, this is not going to give me a 0 in the denominator. So this is good to go. So now I can finally drop my limit notation and actually just evaluate this limit. So now I get negative 1 over x times x plus 0. So that just comes out to negative 1 over x squared. And so remember, we have to use the formula definitions for this, but if I actually think about with the derivative rules, what the derivative of this would be, it would be this. So I know that I found the right thing. Okay, so for number 2, remember here, the directions here are to use the formal definition of the derivative or the alternative formula. So I have to use one of these two formulas, and I don't think it necessarily matters which one of these that I want to use. I think it'll just be a little less writing if I use the alternative formula, so you can note that, but if you use the other formula, it's going to be the same technique either way. So I'm going to just write out the alternative formula here. So I've got the limit as z approaches x of f of x minus f of z over x minus z. Okay, so now I'm just going to plug all this stuff in. So I'm going to have the square root of x plus 1 minus the square root of z plus 1, all of this over x minus z. And so now we want to, solve this. And you'll notice right now, if I were to just try to evaluate the limit as is, I will get a 0 over 0. So I can see I have more work to do. And the common trick that you would use in this type of limit would be using something like the conjugate. So if you remember all the limit tricks that you've learned before, this is where they're all kind of coming into play. So if I multiply by the conjugate, I'm going to have, let's see, there's the conjugate, and I multiply it by the top and the bottom. And so now I can just kind of work through all the math here, right? So I've got the limit as z approaches x. So on top, I'm going to get x plus 1 minus z plus 1. That's what the top part will come out as. And then if you've watched my videos before, you'll know that I suggest that you leave the denominator alone. So don't go and multiply it all out, because a lot of times things will cancel out if you just leave it as is. Okay, so now that I'm looking at this, so I can see that these ones are going to drop out. So what am I left with? So I want to kind of cut this down a little bit. So on top here, I'm left with just x minus z. That's what we're left with, right? This x minus this z. So I'll cross all this out. This top part comes out to x minus z. And that matters because this will now cross out with this part in the bottom. So remember how I said don't multiply out the denominator? That's why. So all of that cancels out. And so now I'm left with the limit as z approaches x of 1 over the square root of x plus 1 plus the square root of z plus 1. And hey, look at that. Now we have something where I can plug in my x for the z, so I can evaluate this limit and I won't get that 0 in the denominator. So now, if I evaluate this, so now I've got the square root of x plus 1 plus the square root of x plus 1. And so this comes out to 1 over 2 times the square root of x plus 1. And so sanity check here, one thing that I would recommend that you take a second to do would be just to recognize that this is indeed the derivative of this. So if you use the chain rule, you would find this as the derivative. So don't just do the formula and then say, okay, I'm done. Take a second to make sure that it actually works out. So if you work this out and take the derivative just using normal rules, you'll get that they are equal. So for number 3, now we want to just take the derivative. So we have a bunch of problems now where we just have to take the derivative. So for this problem, so this is really using the quotient rule, and then you have to also know all your trig rules. So if you forgot, here's the quotient rule. You can pause and do whatever you want with that. And then here's just a list of all the trig rules. So just wanted to list those. You can pause if you need them. So let's go ahead now and take the derivative using the quotient rule. So first we take the derivative of the top function. So the derivative of e to the x is just e to the x. The derivative of sine of x is cosine of x. And then I leave the 4x minus 1, I leave that alone. And then I subtract this off, I leave the top function alone. And then I just multiply this by the derivative of the bottom function. The derivative of 4x minus 1 is just 4. And then I divide all of that by 4x minus 1 squared. Okay, so how would you simplify something like this? So I actually just kind of ran this against a derivative calculator. There's like a lot of different ways you can simplify this. So I think that some teachers would say this is probably fine. And actually if you're in my class, I'd say this is fine. But I will show you like another way you could do this. So the other simplification you could kind of make here is you can separate kind of these pieces into two different fractions. So let's see, I've got this fraction here, and then I'll have this other fraction here. And so you can see now by breaking up the two pieces, so what ends up happening then is I can cancel out this 4x minus 1 with one of these factors. So this is going to be e to the x plus cosine of x over 4x minus 1 minus 4 times e to the x plus sine of x over 4x minus 1 squared. And so there you go. Okay, so for 4 here, so I need to use now the chain rule and the product rule, and I also need to know all my trig rules for this one. So this is kind of a
hefty problem to have to work through. Just a quick reminder, there's all your trig rules. If you need them, you can pause the video at that point. So we also need the product rule. So the product rule, I'll show you that one as well. So again, pause if you need it. So, all right. Let's not get too overwhelmed with this. I think it's best to come up with a game plan first. So the way I think about this is I have this function here and I have this function here. So that's really how I want to take the product rule. Now I can see I'm going to have to use the chain rule in these, but we will just cross that bridge when we get there. So let's get the party started. So for the product rule, first I take the derivative of this guy, so I'll do that in green. So now to take the derivative of this, now I have to think about the chain rule, because I don't want to multiply this out to the 20th power, of course. So the outside function would be this thing to the 20th, and then the inside function would be this 3x minus 4. So I've talked about kind of how to break that down in some other videos. You can check those out if you need a refresher. So what I'm going to do first is I'm going to take the derivative of the outside function. So that means I'm just going to bring down the 20. I leave the inside function intact, and then I subtract 1 from the exponent. And now I multiply that by the derivative of the inside function, which is just 3. And this is going to be sine of 5x. So I multiply that now by the other function. So I took the derivative of this one, left the other function intact. We're good to go. So now we can go to the next part of the product rule. So now I leave the first function intact. And now I have to multiply that by the derivative of the second function. Once again, I need the chain rule here. So the outer function is this sine function, and then the inner function, let's see, I'll use blue here, would be this 5x. So the derivative of sine is cosine, and I leave the inside function intact. And then I multiply that by the derivative of the inside function, which would just be 5. So now I've got all the pieces here, so I can just kind of clean this up. So this will now simplify. Let's see, I can multiply this 3 by 20. So that's going to be 60. And then times sine of 5x and then 3x minus 4 to the 19th. And then for the other part of this will be plus 5 times 3x. Let's see, I guess I had the, let me go to the next line. Plus 5 times cosine of 5x times 3x minus 4 to the 20th. And that's as good as that gets. So you can practice some other ones on the product rule and chain rule if you're looking to do more practice with that. Okay, so for 5 here, so this is the good old chain rule, like to the extreme. So we've got the natural log. So if you've watched my chain rule videos, you know that I recommend you start from the outside in. So let's just identify our functions. So I've got the natural log, I've got the natural log, the next one is this natural log, and then I've got 4x. So I'm going to start from the outside, and I'm going to work my way in for taking derivatives. So I've got h prime of x. So first I take the derivative of the outside function. So I start with just what is the derivative of natural log? It's 1 over x. So instead of having 1 over x, I'm going to have 1 over all of the rest of the inside. So that's going to be 1 over the natural log of 4x. Okay, so now we've got that one done. So now let's multiply that by the derivative of the next function. So moving in, it would be this one. So the derivative of natural log is 1 over x, except now I'm going to replace it with 1 over the rest of the inside. So this will be 1 over the natural log of 4x. Okay, now I'm going to multiply that by the derivative of the next function, this one. The derivative of natural log is 1 over x, except now I just make it 1 over the inside. And now finally, the innermost function, 4x, the derivative of 4x is just 4. So there's all my pieces, and you can see by looking at this, the 4's will at least drop out. So now I'm left with this just craziness, madness. So I've got the natural log of 4x, and then the natural log of 4x, and bada bing, bada boom, you're done. Okay, so for 6 here, so this is another good old chain rule here. So it's all about identifying your functions. So the outermost function is sine, the next function in would be e, and then the innermost function is this part right here. So to take the derivative, I want to work from the outside in. So the derivative of sine is cosine, and then I leave all the other stuff intact. So just leave it alone. Okay, so now I'm going to move to the next function, so e. So the derivative of e to the x is just e to the x, except instead of it being e to the x now, I'm going to leave all of the inside stuff intact. And then finally, what's the derivative of 4x squared minus 3? That's going to be 8x. And so there you go. So there's all your pieces. So now we just want to make it look nice. So this is going to be 8x e to the 4x squared minus 3 times cosine of e to the 4x squared minus 3. Okay, so for 7, so I do want to give a little reminder here. So I've got log base 5 sine of 2x minus 1. So just a really quick little cheat sheet here. So we're going to need, here's the structure of the derivative for log base 5 of x. So we'll need this. And then just in case you need it, there's your list of trig derivatives. You can pause the video and write those down if you want. Okay, so my outermost function, I always like to identify from the outside in. Outermost function, my next function in is sine, and then my next function in is this 2x minus 1. So now I've got a game plan to use my chain rule here. So for log base 5 of all this stuff, so normally this would be 1 over x times the natural log of 5. But now instead it's going to be 1 over the inside stuff, okay? So I'm going to have 1 over sine of 2x minus 1, those are all the inside functions, times the natural log of 5. And so now we've taken the derivative of the outside function. So now I multiply this by the derivative of the next function. So the derivative of sine is cosine. And again, I leave that inside function intact. And then finally, the derivative of the innermost function is just 2. Okay, so now I just have to simplify all of this. And there's not like a ton of simplifying to do here. So it's going to be 2 cosine of 2x minus 1 over sine of 2x minus 1 times the natural log of 5. And so that's it. So for 8 here, so we have more chain rule, some more just crazy insanity chain rule. So I want to think about my functions from the outside moving in. So the first function is this 3 to the stuff, right? 3 to the whatever. And then the next one in is going to be this cosine, and then the next one in will be this 5x minus 1. Then just as a quick reminder, in case you forgot, the structure of a derivative that's of this form, a to the x, so in this case 3 to the x, is going to take this form here. So you can write that down if you forgot. Okay, so let's get this party started. So I'm going to have, this will be 3, so this would normally be 3 to the x, but now it's going to be 3 to the inside function. Oops, and let me color code that green. So this will be 3 to the cosine of 5x minus 1 times the natural log of 3. There's my first derivative. So notice I just left the inside function intact. Now I'm going to multiply this by the derivative of the next function. The derivative of cosine is negative sine. And then once again, I leave all that inside stuff intact. And then finally, the derivative of 5x minus 1 is just 5. There you go. Okay, so now I've got all the pieces, so now it's just a matter of simplifying this. So this will be 5 times the natural log of 3. Oops, and I should put a negative in front here. And then times 3 to the cosine of 5x minus 1 times sine of 5x minus 1. So there you go. All right, so for number 9 here, so now we have a little bit of madness here. So we have chain rule, and then inside this chain rule, we just have the quotient rule. Okay, so the thing to recognize here is, so you always want to like take a second just to recognize where are all your functions. So this thing to the 17th is my outermost function, so that's really where I need to start. Now I realize that inside we have this quotient rule, but I'm not going to worry about this too much until I get there. So as far as the like starting this derivative process, I'm going to start with the outermost function, which this is just using the power rule. So I bring down the 17, I leave all of that stuff on the inside intact, and then I subtract 1 from the exponent. So now I've taken the derivative of the outermost function. So I can move on with my life. And so now I need to multiply that by the derivative of the inside function. And so now we need the quotient rule here. So to take the quotient rule, I take the derivative of the top function, which would just be 3, times the bottom function. and then I leave the top function alone, and I multiply it by the derivative of the bottom function, which will just be e to the x. And then I divide all of that by the bottom function squared. So there's all of your stuff. And so now you can see there are quite a few things you can kind of do to this. I think in the answer key, I wrote down kind of something a little nutty for the actual solution. So I want to just kind of walk you through, like, how do you get there? So first of all, let's rewrite all of this so I have the stuff on top versus the stuff on bottom, because there's just kind of a lot going on here. So this is going to take us a moment. So I have 17. I've got 3x plus 1 to the 16th. So I'm just breaking up this part here with the 16th power. And then I've got 3e to the x minus this 3x plus 1 times e to the x. Okay, so that's all the stuff that was on top. And then in the bottom, I technically have this e to the x, that to the 16th, and then also this other e to the x squared. So those were, so taking this e to the x to the 16th and this e to the x squared. So I'm just trying to visualize kind of where I'm at right now, and we're going to make some more simplifications. So now that I'm looking at this, I can see that I can add these exponents here. But look at this guy right here. I can factor out the e to the x out of this. So I'm also going to do that, and I'll do it in the gold just to help you kind of track it. So I've got this 17 times 3x plus 1 to the 16th, and then I'm going to factor out that e to the x here. So what would that leave me with? That would leave me with 3 minus 3x plus 1. Okay, and then in the denominator, I can add those exponents, so I have e to the x to the 18th. So this is cool because now I can see I have e to the x as one of my factors, so I can cancel it out with the denominator. So I'm going to cancel this out with the 17th. Okay, so we're making some progress here. Let's go ahead and make some space. So from here, I'm going to show you, like there's more than one way to simplify this. So the way I would simplify this is actually maybe different from like the way that another back of the book would simplify this. And then just for funsies, I actually looked at how like a derivative calculator simplified this. So I'm going to show you what I found on this one particular derivative calculator that I looked at, just to kind of show you there are other possibilities. But I'll tell you what I would have done. I would have simplified this set of parentheses here, and then I would have been done with this. But I thought I found something kind of interesting on another derivative calculator, so I'm going to show you one other way that you can think about this, which is a little crazy. All right, so here's what this derivative calculator did. So let's just take a look at where we're at right now, and I'll show you this other way you can kind of simplify this. So this is what I've got right now. So it's 3x plus 1, and then I've got this, we'll call this e to the 17x now. Okay, so I looked at just one simplification by another derivative calculator, and what it did was it took this 3x plus 1 to the 16th, this, and it distributed this inside this set of parentheses. So think about what that does now. So if I multiply, I'm really multiplying this 17, 3x plus 1 to the 16th, I'm distributing this in. So if I take that 17 times the 3, that will give me 51. And then I still have this 3x plus 1 to the 16th, okay? Now, for the other part of this, so as I distribute all of this, so there's no number in front here, so the 17 is just going to kind of hang out. But now think about this for a moment. This is 3x plus 1 to the 16th, but then I have another factor of 3x plus 1, so that would now change this exponent to the 17th, like this. And then depending on how you want to do that, you could also, oops, this should be the 17th. So you can leave this in the denominator, and so this is, like I said, one way I saw for simplification. So The weird thing about simplification is that it's not always like something that everybody agrees upon. There can be different ways to do this. So I wanted to show you a way you could get to this. To take the derivative of this problem, so this is an inverse trig function. So just make sure that you recognize, so this negative one here, it's not an exponent, it's actually referring to an inverse trig function. So the outermost function is this inverse sine function, and then the innermost function is this e to the x. Now, if you forgot your inverse trig functions, I have a list of them, so you can pause the video and write these down and review the derivatives. So, okay, let's go ahead then and get the party started. So to take the derivative of the inverse sine, this will be 1 over the square root of 1 minus, now normally this would be x squared, but now I'm going to replace that x with the inside function and square that. And then I multiply that by the derivative of the inside function, which will just be e to the x. So here's all the pieces for this. And so then you just want to make this look nice. So this will be e to the x over the square root of 1 minus e to the 2x. All right, so for 11, to take the derivative of this, so we have the logarithm, and then we also have the inverse tangent function. So first of all, let's just recognize, so this part here, that's my outside function. This part here, here's my inside function. Now, if you forgot those formulas, so I have, here's the kind of general formula for the logarithm, and then you can pause the video and write down, so here's my formula for inverse tangent, and here are the other inverse formulas, so if you want to pause the video and write those down, you can. Okay, so this is going to go like this then. So I have 1 over, so normally this would have been 1 over x, but now instead of it being 1 over x, it's going to be 1 over the inverse tangent function times the natural log of 3. And now I multiply that by the derivative of inverse tangent, which is 1 over 1 plus x squared. So there you go. So to simplify this, there's not really like a ton of simplifying we can do in this case. So let's see. I'll have the natural log of 3 times 1 plus x squared times inverse tangent x, and we'll call that good. All right, so number 12 here. So remember, we're trying to take the derivative of everything, and I kind of threw this in here as a curveball. So if you really know your derivatives, you should know right away the only thing you can do with this is implicit differentiation. And you know that because we don't have that nice little like y equals this equation, right? The y's are mixed into the equation now. So that is your telltale sign that you have implicit differentiation. So first we need to take the derivative of 5xy. So I need to take the derivative of really two things here, right? I've got 5x and y. What I'm trying to say here poorly is that you need to use the product rule. Okay, so 5x is our first function, y is our second function. If I take the derivative of the first function, 5x, that will just give me 5 as the derivative, and then I just leave the y alone. And then I leave the 5x alone, and then I take the derivative of y. Now the derivative of y would just be 1, but then when you take the derivative of, anytime you take the derivative of y, you have to also include the y prime there, right? Okay, so next, now we move on to this negative 2x, so that'll be minus 2 for the derivative, and then plus 3 y prime, because once again I took that derivative of y and set that equal to 0. Okay, so if any of that looks totally foreign to you, I have lots of videos where I break down implicit differentiation, so I highly recommend you check those out. All right, so now I want to get the y primes by themselves. So the things that do not have a y prime, those two things right there, I'm going to send them to the other side. So I have 5x y prime plus 3y prime. That's going to equal 2 minus 5y. And then I need to factor out these y primes on this side. So now I've got y prime times 5x plus 3 equals 2 minus 5y. So my final answer will be y prime equals 2 minus 5y over 5x plus 3. Okay, now I want to point out that your answer also depends on the order that you like added and subtracted things in. So if you decided to take, say, like these terms, so the y primes to the other side, your answer would be flipped. So the equivalent answer, if you got a flipped answer, would be negative 5y minus 2 over 5x plus 3. So those are your two equivalent answers. So notice that I flipped these and I put a negative in front of the whole fraction. So for number 13, so once again, this is an example of implicit differentiation. You know right away because you have these x's and y's all baked into the same equation here. So let's just go ahead and get started with this. So the derivative of 4x squared is 8x. The derivative of 2y squared will be 4y, except since I took the derivative with y, I have to write a y prime here. Okay, so now for the next one, this xy. So just keep in mind we really have two functions here. I have the function x and the function y, so I have to use the product rule here. Now, the derivative of x is just 1. So this will be 1 times y, so I can just write y. And then, as I move to the other function, I leave the x alone, and the derivative of y would just be 1. However, I also need to write the y prime here. So this is how this piece here is how this shakes out. And I have a lot of examples of implicit differentiation if you're not sure about that. And then finally, the derivative of the derivative of sine of x is cosine of x. Okay, so now the name of the game here is to get the y primes kind of isolated. So the things that do not have the y prime in them, I want to bring them to the other side. So this becomes negative 4y y prime plus xy prime. This is going to equal cosine of x minus 8x minus y. And then I want to factor out that y prime from the other side. And now I can divide by that to get y prime equals cosine of x minus 8x minus y. And I'll flip the order here, x minus 4y. Now, if you look in the solution for this, I actually have kind of everything the opposite. So it also, like, your answer will also depend a little bit on like how you add it to the left or to the right. So the equivalent answer of this would be to have y plus 8x minus cosine of x over 4y minus x. So notice how I just flipped the positive and negative signs. Those are equivalent answers. So for 14, this is another implicit differentiation. You can tell right away because you've got x and y in your equations. That's the only thing you can use to take the derivative. And this one's a little tricky, I guess, because you have to use the chain rule here. So notice that when I use the chain rule, so my outer function would be this sine, and then my inner function will be this xy. And when you get to the xy, we're going to have to use the product rule, but let's just go one step at a time here. So let's start by taking the derivative of sine. So the derivative of sine is cosine. And then remember, you leave the xy intact. Now notice when I took the derivative of cosine, I was not explicitly taking a derivative of like y. So there's no y prime that comes into this right now. Okay, so now what I need to do, I need to multiply this by the derivative of xy. Now you want to view xy as two separate functions because you're going to use the product rule here. So you have x and you have y. Okay, so using the product rule, I take the derivative of the first function, x, and that'll just be 1. So that just leaves me with y. And then for the second function, now I leave the x alone and I take the derivative of the y. That would just be 1. But remember, when you explicitly are taking a derivative of y, then you have to include a y prime or a, you can use y prime or you can use dy, dx, tomato, tomato, doesn't matter which one you want to do. Okay, so there are the pieces of that derivative. And then this is going to equal 0 because the derivative of 3 is just 0. Okay, so now we have to isolate this dy dx and solve for that. So what you want to do now is distribute this. So don't get confused. Remember this xy, this whole xy belongs with this cosine. So I can't multiply anything into this, okay? So what I'm going to do is I'm going to put that first y in front. So we'll call this y cosine xy plus, I'm going to put the dy dx in front this time, and then x cosine of xy, and this equals 0. And I'm putting this in front. To me, it's just like a nicer visual cue in this particular problem. I don't know, it's like a preference I have. Okay, so now I'm going to take that part to the other side so that I can continue to isolate my dy dx. So I've got dy dx cosine xy equals negative y cosine xy. And then I can just divide out that x cosine xy. So this will be dy dx. My derivative will be negative y cosine xy over x cosine xy. And then, hey, look at that. The cosines actually drop out. So my final answer is just negative y over x. So that's it. Okay, so for number 15 here, so this is a chain rule problem with like other chain rule problems kind of stacked into it. So I always think it's best just to start with your outermost function. So here's my outermost function, and then my inner function is this whole thing. So I'm going to worry about what to do with this other chain rule when I get there. Let's start with this little kind of path I've set up for myself. So I start by bringing the 5 down. I leave the inside function intact, and I subtract 1 from the exponent. And now I'm going to multiply that by the derivative of the inside function. Okay, so the derivative of 3 is just 0, so I don't have to write anything down. So now I have to worry about taking the derivative of this guy here, and this is where the chain rule comes in again. So this sine is the outer function, the 4x is the inner function. The derivative of sine is cosine, and I leave the inside intact. And then I multiply that by the derivative of the inside function, and the derivative of 4x is just 4. Whew, okay, and so, oops, and so let me close this with the right color. Okay, so there's all my pieces. All right. So now we just have to kind of multiply some things together. So what can I multiply together? So as I look across this, the 5 times the 4 I can multiply together. So this will be 20 cosine of 4x times 3 plus sine of 4x to the 4th. Okay, so for g of x here, so I've got so this one's a little tricky actually. So I've got tangent squared of e to the 5x. Okay, so very important thing to note. Tangent squared x means tangent of x squared. So one recommendation I make when you see that is to rewrite the problem, because that kind of reframes it in the order that you need to use your chain rule in, because now you can really clearly see that outside function. So the outermost function then is this thing that's being squared. The next function is the tangent function. The next function is the e function, and then the last one is this 5x function. So there's a lot of functions here, right? Okay, so let's go ahead and take some derivatives then. So if I take the derivative of the outermost function, I use the power rule. So I bring the 2 down. I leave all the stuff inside intact. And then I subtract 1 from the exponent, so I just don't write an exponent there. Okay, so next I take the derivative of tangent, which is secant squared. And then I have e to the 5x, okay? Then I multiply that by the derivative of e to the x, and that would just be e to the x, except I once again leave the inside function intact. And then finally, the derivative of the innermost function, 5x, is just 5. So there are all my pieces, and now it's just a matter of making this look nicer. Okay, so it looks like I can multiply that 2 and that 5 together to get 10. And then after that, it's just really a matter of writing the rest of this stuff down. Like this, and this is really as good as it gets. So there you go. Okay, so for this one, we're being asked to find the equation of the tangent and normal lines for x squared plus y squared equals 4 at the point 0, 2. So tangent line, tangent, derivative, those two words really go hand in hand. So I have to take the derivative of this equation here, and I have to use implicit differentiation because x and y are in the same side of the equation. So I'm going to have 2x plus 2y dy dx equals 0. Okay, so I had to write dy dx because I took the derivative of y. If you're not familiar with that, I highly recommend that you go back and you watch some of my videos on implicit differentiation because I break all that down. So now I need to solve for dy dx. So I have 2y dy dx equals negative 2x. And then I can divide out the 2y to get that negative 2x over 2y. So here's my answer. The 2's will cancel out. So I'm just left with negative x over y. Now, I am not done. What does this represent? This is my slope. So this is my m. This is the slope of my tangent line. This is how I would find that. And so what I need to use then to find the actual slope is the point I was given. And notice I have a x and a y coordinate, so I'm literally going to plug the x and the y into this. So when I do that, my m is going to equal negative 0 over 2. And what does that equal? That just equals 0. So what type of lines have a slope of 0? Well, those are horizontal lines. So we'll just kind of note that. All right. So then I want to know what is the horizontal line that runs through this point. Well, it would just be the x coordinate. So actually the line that we're looking for in this case would just be x equals 0. So I literally just take this x coordinate. Okay, so now I have to think about what about the normal line? So what makes a line normal to a tangent line? So it's got to be perpendicular. So what lines are perpendicular to horizontal lines? Vertical lines, right? And so how would I find the vertical line from this equation? Well, it would literally just be the y coordinate. So the normal would just be y equals 2. So this one was actually kind of simple in the actual math that you had to do, but it is a little bit tricky because you have to know what these lines are by kind of looking at them. But those are your solutions. So for number 18, it says find the equation of the tangent line to f of x equals the square root of x at x equals 4. Okay, so tangent and derivative really go hand in hand. So what I want to do is I want to take the derivative of f of x, which will be 1/2 x to the negative 1/2. And now I need to figure out the tangent line at this point x equals 4. So what I need to do then is I need to plug 4 into my equation for the tangent line. So let's see, I'll write this as 1 over 2 times the square root of 4. How about that? Okay, so this becomes 1 over 2 times 2, so this is 1/4. So what does this actually mean? This is my slope for my tangent line. So this is like the m in my point slope equation. So now what I want to do to find that tangent line is I want to plug in all the information that I've got into this. But you're going to notice now there's a problem because I've got my m and I've got my x, but I don't have a y coordinate to put in here. So this is actually incomplete information. So the other thing that we have to figure out here then is what is just f of 4? F of 4, if I just take the square root of 4, that's equal to 2. So this is going to be the y1 in this equation. So at the point 4, we also have the point 42. So you have to keep all this information straight. And it might take you a second to wrap your head around this, but this is like one of the most important things about derivatives. Okay, so now I'm going to have y minus 2 equals 1/4 times x minus 4. Okay, so let's put this into slope-intercept form. So if I distribute this 1/4, I'm going to have 1/4 x minus 1. And then if I add the 2, I get y equals 1/4 x plus 1. And so there's your tangent line. All right, so for number 19, it says find the equation of the tangent line that of the line tangent to x plus the square root of x that has the slope m equals 3/2. So the information in the last couple of questions, I keep just kind of tweaking it, and this is really trying to test how well you understand a tangent line and all the information that goes into the derivative. So first things first, of course, we have to take a derivative. And so if I take the derivative, I'm going to have 1 plus 1 over 2 times the square root of x. Okay, So in this case, I know that I want my tangent line to have a specific value. That value is 3/2. So what I want to do is I need to figure out at what point would I have this value. So what would my x have to equal so that this would equal 3/2? So if I subtract off the 1, I get 1/2, 1 over 2 times the square root of x. This will now become 1/2, so I subtract off that 1. So now I can multiply both sides by 2 to get just 1 over x will equal 1. And so then what you'll get is the square root of x just equals 1, so that means that x has to equal 1. Okay, now try to think about what is the goal here. So we know the slope, and ultimately what we're going to want to use is this point slope form, right? So we want to use this guy right here. So think about all the information you need for this. You need a slope, which we have, but you also need an xy coordinate. So right now all I have is that x coordinate, so now I have to figure out what is the y part of that coordinate. And to figure out the y part of the coordinate, I have to come back to the original function. So let me just note x equals 1 here, and I'll clear some space. And so now I just need to plug in f of 1. So this is 1 plus the square root of 1. So this will equal 2. So I have the point 1, 2. Okay, so now I have all the information I need so I can use my point slope form. So I can plug all this in. So this becomes y minus 2 equals 3/2 times x minus 1. So I want to put this into slope intercept form. So let's keep going with this. So I have y minus 2 equals 3/2 x minus 3/2. So if I subtract, or if I add the 2 to each side, so remember that's 4 over 2 is a fraction. So this will be 3/2 x plus 1/2. And so then there is my equation of my tangent line. Okay, number 20. Find any points on the function f of x equals 2x cubed minus 3x squared minus 12x plus 8, where the tangent line or lines would be horizontal. So think about what it means to be a horizontal line. What does that say about the slope? Because tangent lines and slopes really go hand in hand. So horizontal lines have a slope of m equals 0, so that's going to be important. Okay, so first things first, we know we need to take a derivative. And so this is going to be 6x squared minus 6x minus 12. So I want to know, if I want to know where the horizontal lines are, or, you know, where the tangent lines are horizontal, then I really need to set this, which represents a slope of a tangent line, I need to set that equal to 0. So this will be 6x squared minus 6x minus 12. I'll set that equal to 0. And so now I can just see if I can factor this, right? So let's see, this will be 6. I'll factor out the 6, and so I get this. So then I get 6 times x minus 2 times x plus 1 equals 0. So the points where this would occur would be at x equals 2 and at x equals -1. Those would be the 2 points. And, you know, it could be, to me, this is good enough, but maybe, you know, your instructor, the other thing you could have to do is go back and plug them in. I think saying that this is where this occurs is fine, but, you know, some people have different preferences. So 21 is just kind of getting us warmed up to think about some application problems. What is the difference between velocity and speed? So speed is really just the absolute value of velocity. That is all I was really looking for that question. Okay, so for this question, we've got a rock is thrown off of a cliff that is 48 feet high, and it's got this initial velocity of 32 feet a second, and the height in feet of the rock above the ground, t seconds after the rock is thrown, is given by this equation here. So you have a couple questions in this. The first is, when does the rock reach its highest point? So the scenario that we're talking about here is we've got this rock and we throw it off a cliff, and it goes like this, and then at some point it hits the ground. So if you think about how this shape here works, at some point it's going to hit this top point. And so think about, like, this is a parabola. And so think about now the tangent line at this point. The tangent line at that point would be horizontal. So that is actually what we're looking for when we're looking for the highest point. Where does that tangent line get horizontal? Because after this point, the rock is going to come back down to the earth, okay? So, of course, I need to take a derivative in this. So this will be negative 32t plus 32. And so if I set that equal to 0, I can see that I can just factor out the 32 to get t minus 1 equals 0. So I get t equals 1 second. So in 1 second, the rock hits its highest point. And then the next question is, what is the height of the rock at the highest point? So this is where you have to go back and understand this function. So the height is given by this function. So t is the amount of time, and then if I plug that in, that gives me the height. So really all I have to do for this question then is plug in that 1. So this will be negative 16 times 1 squared plus 32 times 1 plus 48. And so if I plug all of that in, I get 64 feet. Okay, so now C, what is the velocity of the rock when it strikes the ground? Okay, so once again, kind of returning to our little picture here. So we're talking about when the rock hits the ground, but velocity has to do with the first derivative of our function. However, velocity is not going to have anything to do with hitting the ground. Velocity has everything to do with speed. So the original function, this tells us the position of the rock. So at what point, what would the value of this function be when the rock hits the ground? How high above the ground will it be? It will be a height of 0 above the ground. So to solve this, first I actually need to take the initial function, or my little s of t. I need to take this and I need to set this equal to 0. And that will give me when the rock hits the ground. Okay, so I'm going to factor out the 16. And let's see, that's going to give me this function. And so then I can factor this as t minus 3 and t plus 1. So I get either t equals 3 or t equals negative 1. So we're thinking about time here, right? So time can't be negative, so I discard this value. So after 3 seconds, the rock is going to hit the ground. So it hits the ground in 3 seconds. Okay, so I needed that information, so now I can put that into my velocity equation, so I need to clear some space. So my velocity equation, let's see, my velocity is just the first derivative of my position function. So this is negative 32 plus 32. So now I just plug in 3 for this. So if I take s prime of 3, I'm going to get negative 64. So that will be negative 64 feet per second. So that's the velocity as it hits the ground. And then the next question here is, when is the speed of the rock increasing? So this one's a little bit tricky actually when you think about it, because if we think about just intuitively here, so here's that way the rock is moving. So remember, like as we're going up, you might think, oh, speed is increasing because it's going up. But think about just the slopes. So let's say that right here, this is like the top portion of my parabola. So think about these slopes. So the larger your slope, the more inclined your line will be, right? So this line has a much greater incline than this one, right? This second one that I drew. So the slope, as we get closer to this point here, it gets more and more shallow. And so if it's getting shallower, then the absolute value of that slope is actually going to be smaller. So this is a much higher slope, like higher number slope from an absolute value standpoint than here. Okay, but now if I want to continue that logic, so let's say now that I get on this side. So I know that the rock is going down, but just think about in terms of the actual just numerical value of these slopes. and we're taking the absolute value, right, because we're talking about speed, these get more and more sloped. Like they're a much more intense, what's the word I'm looking for? It's a greater incline, so it's going to be a larger number as we go down this way. So at that 1 second mark, the actual like absolute value of our slopes gets larger. So the speed is picking up after 1 second. So I know that these are negatively sloped tangent lines. However, if I take the absolute value of them, just they're getting larger and larger from a speed standpoint, and so the speed will be increasing. And that does make sense, right? So as it hits that top point, as it starts to come down, it's going to gain more and more speed until it hits the ground. So you can kind of also intuitively understand that. All right, find the fourth derivative of f of x equals sine of 3x minus 4x cubed plus 2x minus e to the x. Okay, so let's just go ahead and start this. So with sine of 3x, so I have to use the chain rule here. So if I use the chain rule, that'll be cosine of 3x times 3, and then minus 12x squared plus 2 minus e to the x. Okay, so now let's take the next derivative. So I'll take the derivative of the previous one. So let's see. Now this is going to be 3. I'm going to pull this 3 out in front, and then I know I'm going to have to multiply by another factor of 3x. So I'll just put that out in front. So all of that times negative 3x minus 24x minus e to the x. Okay, so let me just clean that up a little. So this is negative 9 sine of 3x minus 24x minus e to the x. Okay, so now I've got f triple prime. So this will be negative 9 times 3 cosine of 3x minus 24 minus e to the x. And now for the fourth derivative. So let's see, this right here, this came out to what, negative 27? So now I'm going to have negative 27 times 3 times negative sine of 3x minus e to the x. And so if I just clean all that up, this now becomes positive 81 sine of 3x minus e to the x. Okay, and a word problem for our very last problem. So a spherical ball is inflated at the rate of 15 centimeters cubed a minute. At what rate is the diameter of the ball increasing when the ball has a diameter of 5 centimeters? Okay, so one thing that we need to know is the volume of a sphere. So that's V equals 4 over 3 pi r cubed. And okay, so notice that we were given this rate. So this is talking about a volume rate, right? Because we've got this centimeters cubed. And we know this is a rate, right? Because it's literally given to us as a rate. So this is referring to the rate for dv dt. So it's the volume with respect to time. So there's the volume with respect to time. Okay, so that gives us some insight as to what we need to do. And then it says, at what rate is the diameter of the ball increasing? Okay, so that's interesting because this is like the typical formula for the volume of a sphere. So now what we're going to want to do is just kind of change the way that we're thinking about this. So the radius, if I wanted to write it as a diameter, that'll be V equals 4 over 3 pi times 1/2 d cubed, right? And so let me just simplify that a little bit now. So this is V equals 4 over 3 pi times 1 over 8 d cubed. So I can rewrite this whole formula now as 1 over 6 pi d cubed. So that matters because we're talking about diameter here. Okay, so let me clear a little space. Okay, so we're talking about the rate of the diameter. So ultimately what we're looking for, this is talking about dd dt. So maybe I should call this, I'm going to call this capital D, just so that we can tell what the difference between these things are. So I'll call these capital Ds. Okay, so we are trying to find the rate that the diameter is increasing when the ball has this diameter. Okay, so now what this means is I need to take a derivative, right? Because that's the only way I can bring rates into this. And I need to take all of my derivatives implicitly. So this will be dv dt equals 1 over 6 pi times 3d squared dd dt. Okay, so I need to simplify this. So this becomes dv dt equals 1/2 pi d squared dd dt. And so now I have all the info that I need to finish this. So we already said that this was my dv dt, and then we're talking about the moment when the diameter is 5 centimeters. So this is going to go where the diameter is, and then that's going to allow me to solve for this other rate that I didn't know. So I have 15 equals pi over 2 times 5 squared dd dt. Okay, so let me clear just a little more space. So this is going to be 15 equals 25 pi over 2 dd dt. So then if I solve this, I get that dd dt is going to equal 30 over 25 pi. So then I can simplify that into, let's see, 15 over 5 pi. And so there would be, divide by 5. So this would be 6 over 5. My bad, I can't. Joke's on you guys, I can't do math. Just kidding. Okay, so then I get right. 30 over 25 pi, which will reduce to 6 over 5 pi. So there's my rate. And so then this would be a rate of, as far as the units go, centimeters a minute. And so that's that. Okay guys, so that wraps it up for this one. So I'm super curious to know if you have any other questions, or if you've been using this, if you find this helpful. So any comments or likes that you give me is really great feedback. And otherwise, I'll talk to you guys next time.